Okay, we start now. We are discussing about this HMM, hidden Markov model, right? So we have the sequence of vectors like x1, x2, x3. So in this case, I have chosen only 3 vectors getting generated from this model. We have a sequence in it. I mean, this is the first vector, this second vector, and third vector, right? So these are actually getting generated using the state, right? So we can say that we have what is called the latent variable associated with each vector, z1, z2, z3. z1 generates the vector x1, right? z1 is the state, right? Is a latent variable. Change in that state happening from to z2, and then the vector x2 is getting generated from z2, and there is a transition from z2 to z3, and the vector x3 is getting generated from that, right? So this x1, x2, x3, they are all the actual vector which is getting generated from this model, and this z1, z2, z3, they are all what we call it as this latent variables. So what are those variables? Basically, either z1 or z2 or z3, right? It is going to be the like a vector. See, for example, in our case, let us assume that we have 2 states. Only 2 states in that. It means that every vector can generate one among the 2 states. If that is the case, z1 can take the value like this 1 0 or 0 1. Even z2 will take like this, z3 will take the value like this. What does this mean? If this z1 takes the value of the form 1 0, it means that, right, it is in the state 1, the first element, right? If it takes the value 0 1, then we can say that it is in the state 2, right? So your z1, z2, z3, right, they are all the latent variable which are responsible for generating this x1, x2, and x3, right? So now what is it? Generating probability. We are actually formulating the generating probability. The generating probability involves x1, x2, x3, right? And then, of course, that also involves the latent variable z1, z2, z3, right? So given the parameters, all the parameters together, we are representing in the form of a theta. What is this parameter? Basically, this theta. As you know, this theta in this case indicate the parameters. What is there in the hidden parameters available in the HMM? So what are those things? So the moment I say that x1 is getting generated from z1 means we need to model them as some PDF. Right. So in this case, for example, if z1 follows, right, it's a state which is having that PDF of normal distribution, right? So which is going to have your mean vector and then described by its covariance matrix sigma 1. And z2, again, it is a latent variable, right? So the vector getting generated from the latent variable z2, in fact, the vector getting generated from this, that is what I'm talking about. It's not z2 as it is. The vector getting generated from z2 that follows the normal distribution with mean mu2 and then sigma 2. And then we have for the state, right? Of course, we have only 2 states available in this, right? So we have this mu1 sigma 1, mu2 sigma 2. Then the parameters, right? So as we are having 2 states, If it is getting generated from the first state, it means that it is having the characteristics of what? mu1 and sigma 1 density function. If it is 0, 1, then the vector is getting generated from the Gaussian density model with mu2 and sigma 2, right? Right? It is like that. So you have to be careful that Z1, Z3, they are all the latent variable. The number of state is actually 2. It is not necessary that I have 3 latent variables and then having what? 3 states. Not like that. You can have the number of states to be 2, but the latent variables are associated with the what? The corresponding vector getting generated from this model. Right? That is what I said. Z1, Z2, Z3, they are all the random vector. It is a variable. Right? It actually takes the outcome of like 1 0 0 1, right? If I choose it as 1 0 0, it means that we have 3 state in it. So now what I am considering is only 2 state. I am considering only 2 state. It means that Z1 can take the value of 1 0 or 0 1. It is like that. It can take, and similarly Z2 can take the value as 1 0 or 0 1. Z3 can take the value as 1 0 or 0 1. So this is of state 1. 1 0 means state 1 and 0 1 means state 2. It is like that. This is what I am trying to say, right? So state means that is actually follows some density function. That is what I am saying. That follows the both the state, right? That follows the density function Gaussian. So we have a mean vector mu1 and covariance matrix sigma 1. And for state 2, we have a mean vector mu2 and then covariance matrix sigma 2. Okay, this is fine. But what is that generating probability? Now, these things, not only this parameter, right? We have other parameters also. What are the other parameters? We have what is called the transition probability. What is the probability that the latent variable changing from Z1 to Z2? There is a transition probability here, right? All the combinations you can explore actually. Z3 by Z2, right? So you have this transition probability, right? So basically it is a change in that state is going to happen. For example, one such example is like this, for example, it is like this, probability of 1 0, right? Given 0 1. Right? What is it actually really mean by that is, it is a change in state from 2. This is a state 2. What is the probability that the state is changing from state 2 to state 1? This is state 1 here. Right? So there is a transition probability happening. Right? So in this case, I have chosen Z2 to be 1 0 and Z1 to be 0 1. So actually Z1, Z2 and Z3 can take any of these combinations of these two, 1 0 or 0 1, like that. So there is a change in the transition of the state happening is what we call it as transition probability. So that is also one of the parameter for this hidden Markov model. So that is actually represented as A subscript ij. It is a transition probability, right? So these are all the things not known. So given this parameter, these are all comes under theta. Theta means all these unknown parameters, whatever I have listed, mu1, sigma 1, mu2, sigma 2, and transition probability. And not only that, what is the probability that the first state, I mean the vector x1 is getting generated with some state, right? So that is also needed, right? So we are interested in knowing that is represented as what? Pi 1. If I have only 2 states, we have pi 1 and pi 2. It means that what is the probability that x1 is getting generated? I am talking about the first vector alone, because first vector needs to get generated from either state 1 or state 2. What is the probability that that first vector is getting generated with state 1 or state 2, right? So that is given by your pi 1 and pi 2. So all these parameters, whatever I have listed now, mu1, sigma1, mu2, sigma2, aij, pi1, pi2, all these variables, as far as two states are considered, this is what I am calling it as the parameter theta. This is what combined together. Every time we cannot write, we are calling this as group of parameters which we are describing that it is a theta. Fine. Back to this transition, generating probability. The generating probability on the day already discussed, right? Given this unknown parameter, right? So let us assume that the unknown parameters are known now, right? So the unknown parameters, as I told you, that have the parameters like mu1, sigma1, mu2, sigma2, transition probability, right? Aij. If it is a two state, then we have only this a11, a12, a21, a22. Only two state is considered here, right? And then of course we have this prior, right? Pi1 and pi2, right? So these probabilities, right, grouped together, we say that it is theta, right? So this is theta here. So given this theta, you are given this theta, right? Given theta, what is this probability? This is what we call it as the generating probability. Probability of x1, x2, x3, z1, z2, z3, given theta, right? So this is what we need now, right? So how to do that? First of all, what is the probability that of z1, right? The latent variable z1, because z1 is a latent variable which is responsible for generating x1. Being in that state z1, what is the probability that x1 is getting generated from z1? That event is needed here to be included. And then there is a transition happening, right? We have this z1 to z2, the state transition is happening. There are latent variable state from z2 to z1 to z2 is happening. And then being in z2, x2 is going to get generated with what? z2, right? And then again, transition is going to happen from z2 to z3. And then we have this x3 getting generated with what? Z3. So these things, these events combined together, they're all the independent event. So we are multiplying as it is. And this probability, when I multiply all these things, which we call this as a generating probability. This is called this generating probability here, right? Given the parameter, that is very important. The parameters are given in this case. The theta is known to you, right? Given this theta, this is what is known. And remember that z1, z2, z3, I'm using z subscript 3 doesn't mean that we have three state. So this mistake, normally you interpret like that, three states. No, not three states. That's very important, right? This is not three state, right? So this 1, 2, 3 indicate the latent variable associated with the random vector x1, x2, x3, right? So your z1, the length of the vector z1 only determines the number of state, right? So suppose that if I have z1 as 1, 0, 0, we say that it is three state, right? So in this example, we are considering that z1 as what? Either 1, 0 or 0, 1. So it means that it is actually two state, right? If I want to represent the same z1 in three state, z1 can take the value like this, either 1, 0, 0 or 0, 1, 0 or 0, 0, 1. So these are all the three possibilities you are having for z1. It means that it is having three state in this case. But in this example, we are going to consider only two state. So Z1 can take the value of this form. Either it is take the value as 1 0 or 0 1. So it is like that. Okay, fine. Now, what is that our objective? Our objective is to actually find out this unknown parameter theta. First of all, we need to know this unknown parameter. That is called hidden Markov modeling. You are going to do this model. We would like to know these unknown parameters. Once these unknown parameters are known, then we can make use of this generating probability to identify what that sequence is. Last class we discussed about that, right? So we need to know about. Okay, right? So now interested in finding out this unknown parameter, right? Using this HMM technique, how that is done. So what is the objective function in our case, right? So the objective function is this of generating probability, right? This is the generating probability, right? This you would like, that is the thing. You are trying to maximize that as an average case. As an average case, as logarithm is an increasing function, you are using that ln here. So our interest is maximizing the generate probability, that is probability of x is this is written in short. These two are same. This is same as that of this one only. So instead of writing x1, x2, x3, z1, z2, z3, it is written as a shortcut, right? So this probability of x, z given theta, right? That is what you need to maximize. But as logarithm is the increasing function, we are making use of this property ln. Ln of this is we are interested in maximizing that. And not only that, we are going to maximize this as an average sense. It means that you are going to do this maximization over all values of z, right? Given a data means given x. You are given a data, generated data alone is known to you, right? Z is actually not known to you. The corresponding latent variables are not known. I told this probability of z1, right, for generating x1, but we don't know what is that z1 value. Z1 can take either 1 0 or 0 1. So we need to do this one as an act, right? What if z1 1 0? What if z1 is what 0 1? We have to take into consideration all the possible combinations, right? And that is what mathematically what we are writing here is we are going to find out the expectation of the function here. This is the function which is basically the logarithm of the generating probability, right? Probability of xz given theta is the generating probability, right? And then you are taking this logarithm and then you are taking expectation. This is very important key point in HMM, right? I mean, as far as this discussion is considered, this is what we are the important key point, because this is the key step where we are interested on. We are interested on getting this theta. That is the goal. We are interested on getting this theta by maximizing this. This we need to do what? Maximizing this. And that is the whole story. How you do this maximization is in your control, right? So you can, the problem formulation is done. Hidden Markov model problem is done now. But now you are going to solve it. You can use any method to solve, right? You can use even computational intelligence to solve for it. I mean, but the classical statistical method, that is what we are going to discuss now. How to get this parameter theta, that is the whole story. How to get this parameter theta. Parameter theta means mu1, z1, mu2, sigma 2, transition probability A11, A12, A21, A22, and this prior, right? Pi 1, pi 2, everything together is what we call as theta. This one, how you get, because that is the whole story about. We are interested in knowing about this parameter. Once you know this parameter, your job is done. You need to know about this parameter such that this is getting maximized. That is the whole story of this hidden Markov model. Hidden Markov model tries to maximize this. I will write once again here. right? So this is very important, right? So we have this ln p of x is given theta, right? So this is what I would like to maximize. How to get these unknown parameters? Just by maximizing this, right? Fine. So now to do that, we have to look for this generating probability expression. This is the generating probability expression which we have written little earlier, expanded version, right? So in that, for three vectors x1, x2, x3, we know that this is the generating probability, what is given in that first row, which can be written in this form. This pi is the product, right? So it is written like this, no? Z2 given Z1 is written as what? ZL given ZL minus 1, where L is equal to 2 to 3. I mean, this expression is written in by introducing a variable called K and L, right? So nothing else. It's very simple thing, right? When you put K equal to 1, you get probability of X1 given Z1, right? So when you put K equal to 2, you get probability of X2 given Z2. Here it is there, right? And when you put k equal to 3, you get probability of x3 given 3. That is here, right? Okay. And then when you put L is equal to 2, you get Z2 given Z1. So it is here. When you put L equal to 3, you get Z3 given Z2. That is here, right? And this probability of Z1 is here, right? So this is written in this form. So we need to now substitute in this expression with this unknown parameter, right? How to do that? Let's start with one by one, right? Let me start with probability of Z1. What is that probability of Z1, right? We need to, we know that Z1 takes, you have to understand carefully, Z1 takes either 1, 0 or 0, 1. Suppose that if Z1 takes 1, 0, probability of Z1, right? So let me put probability of Z1, if it takes 1, 0, right? So it is pi 1. Suppose if this probability of Z1 takes 0, 1, right? Then the value is going to be pi 2. This actually is described by the actual value of your Z1, right? So how do you write that? The trick is, the idea is, what you are going to do is, you are going to write as a product pi 1 and pi 2, and then you are going to put the power as, right, the elements of this Z1. Elements of Z1 is Z11 and then Z12. It's as simple as that. Because if this Z1 takes 1, 0, this is Z11. This is Z11, and this is going to be your Z12. In that case, when Z11 is 1 in this will be pi 1, right? And here pi to power 0 come, and this becomes 1, right? This becomes 1. So, and hence the result will end up with what? Pi 1, right? So this is a trick we are going to adapt here, right? Once again, let me tell you, the trick is very simple and it's very important also, right? So what we are really doing here is, we are writing this probability of Z1 in a different way, right? Using this trick. What we are going to do now, this probability of Z1 is written as the product. This symbol is the product symbol, k equal to 1 to 2, and this is this prior probability pi, right? So pi k is at 1k, right? Z 1k means the element of Z, right? So is to indicate that number of state. So this is the way how we have written for this probability of Z1. As you know, we are interested in maximizing this. This is one of the term in this expression ln. The all the terms actually, right? We have now started doing that one first term. Remember that we need to do this one for all the terms, right? So let me do one by one, right? Now we have taken only this term. Then we will take this term. Then we will take this term, right? So these three steps are needed. We need to do one by one, right? Now what I have done is only that the first term. The first term probability of z at 1, right? So for every term, what you have to do is you have to take ln. When I take ln, all these things are product, right? These are all the product only, isn't it? So these are all the product. This becomes sum when I take ln, right? So these are all the product now. When I take ln, all things become sum. So one by one we are going to do, right? First we will take ln p of z1. So when I take logarithm of this, right? So what is that you will get? This is again, we have a product in this. So if I take this logarithm of the first term is what actually I am considering, right? So that actually becomes now, the product will now become summation, right? Summation k equal to 1 to 2, and we get what? Z1k, right? Let me write at the bottom, that will be better. That is equal to summation k equal to 1 to 2 Z1k and ln pi k. That is what actually we will get, right? So now we have taken this ln, and then now we are interested in getting this expectation over z. So the variable is z here. This is what we are going to take this expectation over, because this pi k and all is not going to relate. This is going to be that not related with this latent variable z, right? So these are all prior things. So we have to take this expectation of z1k given x. Given x, we have to take this expectation of z1k, right? So, but what is it? Z1k takes the value. See, z1. So this is again another interesting point, right? Z1 is actually having two elements, which is z11 and then z12, right? So depends upon k, you get either z11 or z12. Let us take k equal to 1 now. So in that case, it is just z11. Okay, so z11 means what? It either takes the value 1 or 0. We have only two choice for it, right? So one interesting observation is, suppose if I have a random variable, I just tell you that if I have a random variable x that is discrete, that takes the value, for example, 1 and -1, right? So if I want to take this expectation of x, okay, 1 and 0, I'm sorry, let me put it as 1 or 0 in this case. So what is that you have to do? You have to do that 1 into probability of x equal to 1 plus 0 into probability of x equal to 0. So this is basically the expectation of x. This is one interesting point to tell. It's very interesting to observe also. If I have a random variable that takes the value either 1 or 0, and if I am finding out this expectation of x, that will end up with simply this probability of x equal to 1, because this value is actually becoming 0, right? So what I am concluding by this statement is, if I have a random variable, right, in this case, for example, z11, that takes value as 1, 0, and if I am finding out this expectation of z11, that will simply end up with what? This probability of z11 equal to 1. That's it. Of course, if I'm taking this as a conditional expectation, then condition will follow, right? So if I am taking this expectation of this given x, right? So then the probability will have a condition on x, because we are taking the expectation of expectation z given x. That is the way how we are doing in this, right? So if I take this expectation or like this, conditional expectation, because your data is given. So expectation is z given x, z11 is simply the probability of z11 equal to 1 given x. That is what I am trying to tell. Right? So now coming to this slide, you can now get a clear idea. As I told you, we are interested in getting this ln of p of z1, right? And p of z1 is written in this way, right? So if I take this ln, it becomes sigma now. Z1k ln pi k will come into picture. Now you are taking expectation, right? So sigma is taken outside and this expectation is brought inside. So this expectation of this is simply the probability. This expectation is simply the probability, and that probability is probability of Z1k equal to 1 given x. We are introducing a new notation for that, which is gamma. So hereafter, gamma of Z1k means it is probability of Z1k equal to 1 given x. So that is the thing, right? So this is a new notation what is introduced here. Okay. So now what we really got is the first term. The first term after taking this expectation, now it is becoming simply sigma k equal to 1 to 2. 2 means number of state. Gamma of Z1k, remember gamma of Z1k is that is equal to probability of Z1k equal to 1 given x. Okay, so this is the important thing. Right? Ln pi k, you know what is that pi k, right? Pi 1, pi 2. In this case, k equal to takes either 1 or 2. These 2 are the states, right? We have only 2 states in this, so we have like that. So now this is the first term what we actually got. The same Bayesian actually go for the next. What is the next one here? The next one is probability of xk given zk, right? So what is that basically? It is basically a Gaussian density function. Right? So depends upon the value of zk. Again, suppose my zk is 1, 0. Basically it is zk1. Okay, I'll put it as 1k is at 2k, right? So it is like that. Second subscript indicate the state, right? It is like that. Or let me write it as explicitly for Z1 and Z2. Z1 means Z11, Z12, and Z2 means Z21, Z22 as usual, right? And of course, Z3 means we can have even Z3, right? So if I have Z3, it means that Z31, Z32. But remember that the elements, whatever that elements here we have in the latent variable, all this stuff, right? All these variables, right? So that takes either what? 1 or 0. In fact, if in the vector form, if I take Z1, it takes either 1, 0 or it takes the value as what? 0, 1. Similarly, Z2 also in the same form. And similarly, Z3 also in the same form, right? So this takes either 1, 0 or 0, 1. It is like that. This is the latent variable. The moment you see this Z1 as 1, 0, we can understand that this is getting generated from state 1. If the value is 0, 1, we can understand that it is getting generated with what? State 2. It is like that. Okay, fine. Now, as I told you, what is the probability of xk given zk? What does it mean? It is being in a state zk, what is the probability that vector xk is getting generated from it, right? So we know that xk can generate either from state 1 as well as state 2. Suppose that my zk means k could be 1, 2 or 3, right? So let me put it as zk. Again, zk can take either 1, 0 or 0, 1. If zk takes the value 1, 0, it means that it is getting generated with what? State 1. If it takes the value 0, 1 means xk is getting generated with what? State 2, right? So in that case, both are actually modeled as what? Gaussian density function, the normal distribution, right? So that is the thing you are seeing here. This is the normal distribution here. You see that? This is the normal distribution function, a normal Gaussian density function here, right? So this mu L and sigma L, they are all the mean and covariance matrix of the Lth state. We have only two state here, L equal to 1 and then 2 state, right? So we have only two choice in this. Either xk gets generated with state 1 or getting generated with what? State 2. We have only two choice for it, right? And that is that L value is actually 1 or 2 in this, right? Only one will get activated. How that will get activated? Based on this value of ZKL, right? Only one among them is going to be the 1. The other one is going to be the 0, right? So it is ZK1, then the next one is what? ZK2, right? So the way what I have written here is in this form, right? K is the kth data getting generated, right? And the second subscript L indicate that either it is going to be the state 1 or state 2. So we have only two choice for it, ZK1, ZK2. But we have the outcome like this, either 1, 0 or it is going to be the 0, 1. Only these two are possible. Suppose if it is 1, 0, it means that xk is generated with what? The state 1. If it is 0, 1, xk is getting generated with what? State 2. So it is just a product. Only one thing will get activated here, right? So let me write explicitly like this. What I'm trying to say is this: the normal distribution xk getting generated with the state 1, mu 1, sigma 1. So this is of state 1, right? So here I am writing this zk1. It is multiplied with the same trick, same adopted in the earlier case. Zk given what? Mu 2, sigma 2, power zk2. As I told you, if zk1 automatically zk2 is becoming 0, so this will be activated in this case because this value will become 1, right? So the other way, suppose zk1 is taking 0, right? If this is 0 here and this is 1 here, in that case, this value will become 1 and this will get activated, right? So this probability of xk given can be written like this. That is what I am claiming. The claim is we can write this probability of xk given zk in general like this, and other things are a straightforward max, right? You can take expectation now as usual, right? So when you take this expectation after taking logarithm, this pi, this product, right, is actually becoming now sigma, and zkl is coming here and ln, and this normal distribution, the shortcut I am representing this phi k l, right? Don't get confused. What I'm writing here is phi subscript kl means it is a normal distribution, right, of generating that kth vector from the Lth state, mu L, sigma L, right? So this is the shortcut what we are representing, right? So the whole expression normal, this one is representing shortcut. Yeah, I have written here. KL is this normal, right? So this is what is written here. And then bringing this expectation inside as you know, expectation of ZKL, just like what we had it for the earlier case, we are representing that one as what? Gamma of ZKL. But you know what it is, right? Gamma of ZKL is nothing but probability of ZKL is equal to 1. Right? So just like what we had the previous understanding, I'll write somewhere here. Gamma of ZKL is nothing but probability of ZKL equal to 1 given X. So that is the meaning of it, right? So that is the thing it is written here, right? So now this is about the second term. This is about the second term, right? And then finally we have the third term. This is the third term is the final thing actually. First term is probability of Z1. So that is the first term. The second term is of this form, xk given zk. Second set of terms we can say, it is not only one term because k actually varies, right? And then we have the third set of terms, which is basically the transition, zl given zl minus 1. It is like that. This is the third set actually you are having. Now the same way we have to attack this problem, right? So now what you are going to do is you are going to, right, take this logarithm and then take this expectation. The same method you are going to do now, right? Here in this case, what is a transition probability? Probability of ZL given what? ZL minus 1, right? So how to represent that, right? So that is needed now. So you can see that it's getting highlighted with the elements in it. So it is like, you know, L minus 1th state to Lth state. So that is a transition. It's actually, I mean, L minus 1th vector, right? So let me write that once again. So it is like this. So this is Z1, this is Z2, this is Z3, and the vector X1, X2, and then X3, right? They are getting generated with this Latin variable, right? So what is the probability that you have to change over, right? From where? Z2 to Z3, for example. Z3 and then change from where? Z2. So how do I relate this one with the elements of Z2 and Z3? Right? For example, what are the possible combinations we can have? Z2 could be something like 1, 0, and then let me write Z3 as 1, 0, right? This is one choice we have because we have only two states, right? This is one choice what we take, right? We can write the other choice also now. Z2 is 1, 0, but Z3 is 0, 1. This is another choice, right? We have 4 choice in it, right? Let me write all. Then is 0, 1, and Z3 1 again, right? So this is the third choice. And then finally you can think having Z2 as two as 0, 1 and 3 as 1, right? I think I've done that 1, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1. 710, right? These are the four combinations you are having, right? So what does really it mean? It means that the transition is happening right here, state 1 to state 1, right? And here state 2 to state 1, because there is a movement from Z2 to Z1. That is what this line is describing, right? So in this case, it is of state 2 and this is state 1. It means that state 2 to state 1 in this case. Here, Z1 is of what? State 1, and then Z3 of state 2. 1 to 2 is happening here, right? So this is 1 to 2 is happening. 1 to 2 is happening. And here it is just 1 to 1. And this case, it is 2 to 1. And this one is 1 to 2. And this one is 2 to 2. It is in the same state, maintaining in the same state, right? So this is what you are having. So we have to write this probability in terms of these elements. That is what I'm saying, right? So which element is actually is responsible, which is actually helping in getting this probability? We can actually have a transition probability. Basically, the transition probability is, right? So let us say that the transition is happening from where, right? L minus 1th state to Lth state, right? Okay, so this is the transition probability. What I am showing is the transition probability, right? L minus 1th state to the Lth state here, right? And then we have here this M and N, right? So these are all the M and N element. You can see that all possible combinations, right? Right. So M and N actually describes the state, right? And this one and L is the position here, right? So we have this Z1, Z2, Z3. So what I'm trying to say here is this L describes the sequence 1, 2, 3, right? L takes the sequence like this. L minus 1 means 2, 2, 3, 1, 2, 2. Not about the state. State is described by this M and N. In this case, in this expression. In this expression, that is what it is showing. I repeat once again, if you have not having that clarity. What we are having here is the transition probability, right? So this is what I'm trying to say is probability of ZLM given ZL minus 1 N. Right? This, of course, this is what we call as the transition probability, which we are writing it as A. Of course, we can describe with subscript M, N, and L. What is it really mean by that? This is basically, this L indicate the sequence actually, right? So because it is in the order, right? So we have Z1, we have this Z1, and then we have Z2, and then we have Z3, right? So the movement is actually from 1 to 2 or 2 to 3. It is like that only. It is in the order only, right? So that order is actually described by this L. L minus 1 to L. It means that 1 to 2 is happening, 2 to 3 is happening in this case, right? But which state? That is described by your M and N, right? I hope you are able to understand that. For example, if I am saying Z11, right? So, okay, let me put it as 2, 1, and then this is 1, 2. Say, for example, this is the case, right? So, what does it mean? It means that you are actually moving from 1 to 2. This is the 1 to 2, right? So this is the movement. 1 to 2 is happening, but 1 in the state, 1 to 2 is happening, that is right. but 1 with the state is also 1. The state is also 1 in this. And this case, the state is actually, right, 1 to 2. Yeah, no. This is the state of 2. This is the state of 2 and this is the state of 1. The second subscript indicate the state. The first element, I mean, is at 1, right? So this one, of course, it is generating x1, that is fine. This latent variable z1 is actually taking the state 2, that is the meaning of it, z1, 2 in this case. Right? And then z2, 1 means it is actually moving from where 1 to 2. So z2 is actually the movement, but which is actually in the state 1, right? So this second element of the subscript indicate that it is a state. That is what I am trying to say. It means that your m and n is actually the states. M and n, they are all the state, right? L, there is always a movement from L minus 1 to L, right? It means that 1 to 2, we have a transition, or we have 2 to 3. This is not a state, this is a sequence. L is a sequence, okay? 1 to 2, 2 to 3, that is what is happening. This is a sequence, right? 1 to 2 is happening, then 2 to 3 is happening. This is a sequence here. But 1 to 2 is happening with a particular change of state, right? So that is described by that element m and n. L minus 1, L is actually the sequence, and m and n, they are all the states here, right? So we need to actually represent this one by using this, the corresponding transition probability in this case, right? So that is what I'm trying to say here. Now I hope this is clear to you, and that is activated, I mean, that is described by the corresponding element itself, right? So as I told you, if I write this one with the power, the same element what is there in that probability, within that, that element, if I write it as a power, right, probability of ZLM given ZL minus 1 n, right? Power, I'm writing a power here. Power ZLM, and we have here ZL minus 1 n. It is a product. It is a product in that. And you know that this value is either takes 1 or 0, and this value either takes 1 or 0, right? So any one of these 0, so it is like power 0, it is going to be 1. This will have validity, or this will have some value other than 1 only when both are 1. That is what the idea is. The idea is when this value is 1 as well as this value is 1, then only it will end up with this probability itself. This will end up with this probability itself. This probability is what? ZLM given ZL minus 1 n, right? So when this will happen, when the value of this one is equal to 1 and this value is also equal to 1. So what will happen in that case? You get directly the probability, the corresponding transition probability you will get. So the transition probability is represented as what? A, M, N, L, right? So this will end up with the corresponding A, M, and L depends upon, right, the particular combinations of L, M, and N that gives you both the elements as 1 and 1, right? In all other combinations, what will happen is one of them is going to be 0 because we have only 4 choice, 0, 0, right? 0, 1, 1, 0, 1, 1. 4 choice are there. Only one combination, both are going to be 1. In that case, you will directly get that corresponding transition probability, right? The same trick only. The trick is the same trick, right? So you are writing as a product in this case. That is what I'm saying here. You are writing it as a product, right? Right. So you are having here, right? So and then that product is missed here, and then you are going to take this. The product is missed here. That is the problem, right? You have this product actually, for both m and n. So that is the thing. So you have this product. Please correct it. There is a product here for m and n. So after taking logarithm, that becomes the summation here. That becomes a summation here. So this expression, there is a mistake, right? So we have, after ln, we have to write this product, m equal to 1 to 2, and then n equal to 1 to 2. That is the issue, right? So we have to write this product. After taking ln, as usual, that becomes now the summation. That will get converted into that summation now. And what power that is coming here, and then ln, of course, here we have taken that that product converted into what? The summation in this, right? So here also we need to write this, right? The product is getting converted into that summation part. So we have a summation in this, right? And taking that expectation and expectation brought inside, it will end up with, we have another probability here. This is the probability of the joint, and this is the probability of the condition, right? So I written here, you see that zeta, this is the probability of, with what? The joint probability, and this AMNL is the condition probability. You can see that both are ending up with what? That probability of ZLM, ZL minus 1n only. But in this case, it is a joint, and this case, it is a condition, right? In other words, let me put a summary now at this moment so that you can get a clarity. What we got is, originally we had the parameter theta. This is very important what I'm telling now. We know the parameter theta is pi 1, pi 2, and then we have sigma 1, mu 1, sigma 2, mu 2, and of course this transition probability which we already introduced, which is called your A, M, N, L, right? So, I mean, all possible combinations you can actually have, A, M, N, right? So, right, this is a transition probability. Let me explicitly like A11, A12, A22, and then A22. Yeah, 21 and 22. Right, so these are all the transition probabilities, theta, right? And all of which is of we are interested on, right? Now what happened was, by doing this problem, right, for simplifying this objective function, that ends up with another two parameters which we called as gamma, right? One is gamma z KL, right? So in the first equation, we have what is called gamma of Z1K. Gamma of Z1K was there, and then gamma of ZKL, and then we have what is called the zeta of ZLM and ZLN. So these additional parameters actually we got by doing this, right? So now the parameters are actually increasing, right? So we are interested in finding out this parameter, but this parameter is actually introduced in this expression. And further, you know, for example, for instance, let me take gamma of Z1K. We know that the definition from the previous slide, if we have it as probability of Z1K equal to 1 given X, probability of Z1K equal to 1 given X. So like this, you know, and your gamma of ZKL, this is the definition for that. So that is given as probability of ZKL equal to 1 given X. And then we have the zeta, right, of ZLM, right, and then L minus 1n is given as joint probability of ZLM equal to 1, and then Z L minus 1 n, right, equal to 1. So here it is minus 1 is there. So there is a correction here, L minus 1. L minus 1 n equal to 1, right? So it is that this is L minus 1 n, right? L minus 1, sorry, L minus 1 n, right, equal to 1 given x, right? So now how to solve this? Because we got now the additional parameters also got involved in that, right? The trick to do this problem is actually by using what is called expectation maximization algorithm. I repeat, the problem formulation finally boils down to like this. This is what we are planning to maximize. Now this is written in a very interesting form by introducing a new parameter called gamma and zeta in this, right? So this is the final expression, right? So this is the final expression which we are trying to maximize. We are interested in getting all the unknown parameter just by maximizing this. This is what you have to maximize. Okay, so this is what the thing. So it is rewritten, right, by proper variable, right? Because some cases I am using different notations for the states and the time instant. So it is now properly restructured with a common variable, right? K as the state and N as the sequence. And that will end up with the same expression only, but it is rewritten in a proper form, right? This is the thing which is actually we need to maximize, right? Of course, with the constraint that the summation of pi k is 1 and then transition, right, from k to, right, from the kth state to lth state of the nth sample. N is basically the sequence. N is the sequence, right? So that is not related with that. The nth sequence, that's fine, but there is a transition probability happening from the kth state to lth state. Being in a kth state, you have only 3 choice for it. Being in a kth state, you have only 3 choice for it. Either you can go for the first state or second state, or these are all the 3 L values what you can actually expect. And hence, if I do the summation, that will end up with 1. So now, finally, what you understand is this is the problem statement. What we are getting, this is what, I mean, what is given here. This is what you need to maximize with the constraint. These 2 constraints needs to satisfy, but this needs to be maximize, right? How to solve this, right? So that is the question. How to solve this, right? So to solve this, we are using what is called expectation maximization algorithm. Right? Expectation maximization algorithm. Now I think whatever so far I have discussed, even if you are not very clear, once you go through this video, you may get it clear further. But what I am going to tell now, that is important. So I am going to tell from this point onwards, I am going to discuss about this expectation maximization algorithm for solving this equation. So far, whatever we discussed is actually, right, for getting this objective function only. How to get this objective function for this HMM. That is what we discussed. But now we are actually in the stage of solving it. To solve this, right? So what is it solve, right? So what is that we are going to do in this? What we are going to do is we are going to use this expectation maximization algorithm, right? So what is that? about, right? You are going to get unknown parameters, right? So this theta, that is what the goal, right? Theta is this unknown parameter. So we are interested in knowing about this sigma 1, mu 1, sigma 2, mu 2, and then pi 1, pi 2. And then, of course, we have what is called this transition probability, AKL, right? Right. So, of course, if you want for this case, I can write it as like A11, A12, and then A21, A22. This is the unknown thing, right? So, you are going to, right, estimate these values, right, in by using this expectation maximization algorithm, right, in an iterative manner. What is that iteration is about, right? You are going to maximize, right? Maximize this expression. This is very important what I'm telling now. You are going to maximize this expression, right? So to do this, you are going to differentiate with this unknown parameter. The unknown parameters are like uh, this one, whatever I have listed here, right? Pi k, and then sigma 1, mu 1, A11, A12, all these things, right? We are going to differentiate this one equal to 0. Of course, with the constraint, you know what is the constraint? It should satisfy this constraint and this constraint, right? You are going to differentiate this equation and then equal to 0 with the constraint and get a expression for all this, right? Pi k, sigma 1, sigma 2, all those things, right? In terms of, that is the important thing, in terms of gamma and zeta, right? All this expression, I mean, you after doing this differentiation and equal to 0, all these things, you know, you get a expression in terms of this gamma and zeta, like this. That is the problem, right? So what we have to do is, you have to actually find out some expected value of this gamma and zeta, right? So you have this gamma and zeta, which is called this expected value of this. This is the expected value. I will tell you how to find out this gamma and zeta expected value of that. But as of now, you have to understand what is that expectation maximization algorithm. The expected value of gamma and zeta is what actually you have to identify, which we call this the expectation stage. This is called expectation stage. And then using this expected value of gamma and zeta, why I'm saying this one is, you know, gamma and zeta, you get a expected value of this, right? But this gamma and zeta, for computing this expected value of gamma and zeta, demands this parameter sigma 1, mu 1, sigma 2, mu 2, and so on. Only using this only we can actually find out this expected value, right? Of course, initially we can start with some value, right? So now you are by maximizing this expression, you are getting these unknown parameters in terms of this gamma and zeta. This is what we call it as expectation stage. This is sorry, maximization stage, right? Because you are actually trying to maximize this equation and trying to get an expression for sigma 1, mu 1, sigma 2, mu 2, so on in terms of gamma and zeta. This is called maximization stage. This is the maximization stage and this is the expectation stage, right? So what I'm trying to say here, they are related. We have this gamma and zeta in terms of actually theta, the unknown parameter, this theta. Theta in terms of gamma and zeta. So that is the thing. So what you have to do is, you have to use this old theta. Old means because you are going to solve this one in an iterative manner. you are going to have some guess of this unknown parameter, which is called old. Theta old, let me put it as a old one, right? Theta old. Using this theta means what I'm telling is sigma 1, mu 1, sigma 2, mu 2, pi 1, pi 2, a1, 1, a1, 2, a2, 1, a2, 2. Together I'm calling this theta, right? You have something called theta old. Some arbitrary value you are going to initialize for this theta, which we call it as theta old. And using this theta old, you are going to have a guess of, that is the expected value of this gamma and zeta. Using this gamma and zeta, because you are in the maximization stage, this individual elements, whatever we are having, the sigma 1, mu 1, sigma 2, mu 2, pi 1, pi 2, and so on, all these things actually depends on your gamma and zeta, right? So it is like a iterative process, right? So let me put in a simple form like this. You initialize theta, that is the first step. Initialize theta, right? Using this theta, you are going to actually find out gamma and zeta. This is what we call as initialize theta, means it is basically theta old, right? You get this, and using this, you are going to get the value of mu1, I mean zeta 1, mu1, and so on, which we call this as maximization stage. Now you get a new value of theta now, right? Updated value of theta. Using that updated value of theta, you are actually going for again estimating gamma and zeta. This is in the loop. This is in the loop, right? So let me summarize the expectation maximization algorithm. Of course, we are going to discuss in detail in the next class, but I just wanted to tell you what is an expectation maximization algorithm. Basically, what you have to do is you have to initialize theta. That is the first step. Theta, hereafter I'm just saying theta, but you understand theta means all this vector, right? So it is like mu1, sigma 1, mu 2, sigma 2, everything, right? I mean, of course, the transition probability, right? So we have this a1, a12, right? A2, all those things, right? So all these things we call this as a theta, right? Otherwise, pi 1, pi 2, 1, sigma 1, mu 2, sigma 2, a11, a12, a21, and then a22, right? So all these things we say that it is a theta. Okay, this is theta now. First step is you have to initialize theta. You are going to have some arbitrary value of that, initializing this theta. Using this, you have to go for what is called this expectation stage. Expectation stage means you are going to find out what is the value of gamma and zeta, right? Using this theta, right? So initialize theta, which we call it as theta old. I mean, the current value we can say otherwise. Instead of saying it is a old, you can say that the theta current. Okay, this one you are going to actually compute using what? Theta current. Okay, so now done. Now you have to go for what is called maximization stage. Right? I mean, I put it in the other way around. Using this theta current, I mean, whatever you have here, you are going to actually get this gamma and zeta. And whatever you have this gamma and zeta, it end up with updating theta, right? Right? Now this is in the loop. Then using this theta, you go for the expectation, right? And then using this current theta, you go for this maximization. This is in the loop. The steps 2 and 3 is in the loop. You have to repeat this step 2 and 3 or repeat it until the probability of generation is getting maximized. When there is no significant change in the probability of generation, 2 and 3 are repeated until convergence. We can say in short that until convergence, right? These two steps are repeated again and again, right? So this is what we call it as expectation maximization algorithm. In solving this, in fact, we are interested only in these parameters. This parameters is what we are interested. For getting this parameter, we have to use this parameter, gamma and zeta, right? So for getting this, we need theta actually. That we'll see in the next class, right? Gamma and zeta we have in terms of theta. Theta in terms of gamma and zeta. It is like that. We are getting a relationship like this. By doing maximization, we are getting this, right? All these thetas in terms of gamma and zeta, right? So we need this gamma and zeta. So we are using this expected value of gamma and zeta, right? And then you are computing this theta. Using this theta, once again, you are going to reiterate. I mean, you are going to find out what is the expected value of this gamma and zeta, right? And using that, you get a new theta. This is in the loop until this probability of, right, generating probability is getting maximized when there is no significant change in the probability of generation as the iteration goes on. So once it is getting converged, our requirement is only this theta. So we are not interested at gamma and zeta. Once the theta, we have to take back the theta and the algorithm starts. And this is very popular algorithm. We call this algorithm as expectation maximization algorithm, right? So in this class, what actually we discussed was how to formulate the objective function for HMM with two state, right? By introducing a new variable called this gamma and zeta. That is what we discussed. And of course, we already used the latent variable, right? And we have this phi and k means, right? It is related with what? Your mu1, sigma 1, mu2, sigma. Everything together, we are writing in shortcut as phi. I mean, phi here. Okay, so everything we are writing in a short. Okay, so this is, of course, a lengthy what is that? It's a lengthy process actually, this HMM. Can we use any value for theta in the initial case, right? So we have to initialization itself is a problem, right? We have to initialize, of course, by using the k-means algorithm. As I told you in the last class also, we can actually use k-means algorithm to initialize this unsupervised clustering algorithm to do that, right? So after doing that, then we can come back to this algorithm, right? So initialization is itself is a subject, right? How to initialize and what is that, how the convergence is going to happen with differentialization, right? In fact, otherwise we have to go for multiple initialization and then you have to find out which initialization is giving you the better maximum generating probability. That is the implementation strategy, how we are going to use. But what we discuss is the general groundwork, right? So we got an objective function, and then how to maximize this objective function itself is a great challenge because there are so many parameters available in that. So to attack this type of problem, we have a very nice method, what is called expectation maximization algorithm, where we assume some parameters, right? And then we do this maximization. And then we again, using the new parameters, what we get, we have to reiterate on the expectation stage, right? In this case, gamma and zeta are chosen in the expectation stage. And then for the maximization stage, we have all these parameters. The theta is the parameter. So we have to do this iteratively to get it converged, right? That is the idea. You go through this video once again so that you will get it clear. Next class, you will get still clear only when you see to this video, right? So you go through this video, next class, you will get a clarity on this. We'll stop here.